Welcome, and thanks for joining us. I'm Linda Bell, Editorial Director at TechBriefs Media Group, and I'll be your moderator for today's webcast using spectrum analysis to track, locate, and identify interfering signals, sponsored by Inritsu. Today's webcast will last about 60 minutes, and there will be a question and answer period at the end of the presentation. You could submit a question anytime by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible following the presentation, and those questions not answered during the live event will be addressed following the webinar. In order to view the presentation properly, please disable any pop-up blockers you might have on your browser. So now let's meet our speaker. Russell Lindsay is a Senior Product Manager at Inritsu Company, focusing on handheld test and measurement equipment. He has worked in the test and measurement industry for the past 8 years. Previously, he served in various engineering roles in aerospace and defense, from system engineering and test to R&D design. Now I'd like to hand the program over to Russell Lindsay. Russell?
Great. Thank you, Linda, and thank you, everybody, for taking the time to attend today. Hope you're staying safe and healthy, and if you're working from home or if you've made it into the office. And also, happy Veterans Day to everybody. If there are any veterans that have joined us today, heartfelt thank you for your service to our country. So today we are going to be focusing on spectrum analyzer tools that can help you track and locate and identify interfering signals. Just a brief overview of our agenda. We'll talk a little bit about the problem of interference, where it comes from, why it's important to get rid of it, and then we'll go through some of the sources of interference, and then talk about mitigation steps and tools that you can use to do those mitigation steps. So to begin with, let's discuss the problem of interference. If you look at this chart that we have here, these are frequency allocations in the United States across our radio frequency bands. What you can see here, the overall takeaway from this chart is that spectrum is allocated to many, many users, and it is packed in there because it's a finite usable resource, it's a valuable resource, and it's strictly controlled. So getting the rights to transmit in a specific frequency band is it's a valuable thing. It's used for many commercial purposes, and also it's a very, very important resource for national security. So when it comes to controlling your spectrum and making sure that it is free of interference, not only do you have the right to do that, but the responsibility to make sure that you're using it properly and not going into other people's bands as well. So just in particular, if I'm going to highlight, this is sort of the cellular frequency bands. You'll notice that it's not just a bunch of mobile phones in there. These frequencies are chopped up and allocated and given primary and secondary resource allocations, and so the use of them is extremely important. With interference, the issue here is that in cases where you have critical communications going through your spectrum, interference can come and overwhelm intended signals. It can cause interference as you're transmitting those bits across the air. Interference comes in, causes you to drop bits or have gaps in your communications. So you're basically going to drop in your key performance indicators like throughput or connection reliability. It could block mission critical communications or intelligence, whether intentionally or unintentionally. This interference can pose a great security risk in cases where communications are of national importance. So it's important for anybody who owns and manages spectrum who's trying to transmit over-the-air signals to ensure that their spectrum is free of interference and that they're not interfering with others as well. So now we're going to talk a little bit about some of the sources of interference, and we break that down typically into two categories: random sources of interference and intentional or nefarious sources. Now, random sources are generally your more common sources of interference. These can really vary. You actually be surprised at the wide number of things that can interfere in the spectrum. So you might have legacy or low quality electronics. One of the pictures I have in the top right is an old arc welder, and that's a classic example of a product with an oscillating alternator in there that is creating, that is actually generating signals that can come in and interfere with some of the critical, for instance, the first responders bands, things like that. So low quality electronics, unlocked oscillators, poor filtering. You see a lot of products that are purchased online that come from disreputable or at least not well controlled or regulated manufacturers. And if those products that are designed to receive and transmit signals aren't properly filtered, aren't properly managed from a power level perspective, they are typically going to be risks of interference. You'll see intermodulation interference and things like rusty bolts and loose cables. Somebody might have a wire that they left running that they thought was no big deal. It's coming in and causing the intermodulation. I already mentioned industry machinery, cable TV radiation. As you have cable TV wires that are run through the ground and have been there for years and years, they could have the shielding erode, or they could be cut during construction. And now you have signals leaking out into the air, and surprisingly, those signals can come out and cause a lot of problems in the communication bands. And even light fixtures, things like your neon lights, can cause problems with over-the-air transmissions. So those are some of your random source examples. Intentional or nefarious, these are things like radar jammers. You may have covert signals that are hidden within other signals. So you may be transmitting somebody may be transmitting within an LTE band, for example, or just general bugs where if you have a controlled room, somewhere where you're communicating top secret information, you can find that there may be bugs hidden in the spectrum in those areas as well. So those are typically the sources of interference. A couple of examples. This one, I'm going to leave you hanging with a bit of a cliffhanger, but this is an example of a network operator. They were seeing dropped calls. They were seeing issues with their throughput, and there had been no obvious changes to their environment. They hadn't changed their network equipment. They didn't know of anybody else who had. There weren't any major changes in construction. And so I've teased it on the right, but stay tuned. I'll tell you about how spectrum analysis tools were used to find that one. I will give you an example here of a nefarious source where you have a wireless network operator who had customers who were complaining about network issues in a shopping center or near a shopping center. It was only happening during the day, but they were getting flooded with calls. Well, they sent somebody out with some tools to go and do some hunting in a way that we'll discuss later in this webinar, and they were able to find that one of the shop owners in a strip mall who didn't want his employees on their cell phones during the workday had gone to an online store, purchased an illegal jammer, LTE jammer, and it's not illegal for him to purchase, but it is illegal for him to operate it. And so he was jamming the LTE signals of his employees so that they would stay off their phones during the day. But that was causing network problems for everybody around him as well. And so he was told that he needed to turn that off or face a fine. Okay, so now we're going to go into some ways to mitigate interference. And we typically break interference mitigation up into three different categories. The first category is your spectrum monitoring and spectrum clearing. The next would be signal identification, and then interference location and finding. So I'm going to go into detail on each of those to give you a little bit more information. So first, let's talk about spectrum clearing. So why does somebody want to do spectrum clearing? First of all, as I mentioned before, if you've purchased or been given the rights to transmit in a certain frequency allocation, the spectrum monitoring and clearing is where you're going to go and make sure that on a regular basis that you're not facing any unwanted transmissions within that band. So when you first start transmission, it's typically the first round of information about an interferer. This is where you'll pick up the interference for the first time. So you might do this when you talk about when, you might do this over time. Basically, at first, when you first start transmitting, you might spend some time clearing out. If you have rights to transmit there and you know nobody else does, before you start transmission, this is an opportunity for you to basically set out and monitor the signal, watch it over time to make sure that you're not seeing anything pop up that you wouldn't expect to pop up, and then eventually being able to, if you do see things, then we'll get into our next steps for identification. So this can be done either before you do or if after you start transmitting. Still, you may want to ensure that only those signals that you expect to be transmitting are being transmitted. If you start to see some complaints about performance, spectrum monitoring can be an opportunity for you then to go back and look and see what's happening over time. So this can be done through basically just monitoring. You can have regular dashboards that monitor your key performance indicators like dropouts, disrupted communications, throughputs, things like that, or spectrum clearing, spectrum analysis tools. So a couple of examples for a real-world example for spectrum clearing. This is a cellular example, but I think it applies to anybody who has been given resources. In this case, recently in the United States, T-Mobile spent almost $8 billion for the right to transmit 5G in this 600 megahertz band. In this case, their interest obviously is protecting that dollar investment. If you're in a situation like maybe you're in a defense application, it may not be that you so much spent money on it, but you've been allocated that resource and you have value in making sure that those communications that are of national security importance are not interfered with. In this case, that band that T-Mobile bought was previously used by broadcast televisions, and so you see here this little article that talks about spectrum repacking. Essentially what we're saying here is that those broadcast network stations that were in those bands were asked to move. These are various regional broadcasting stations that you never know for sure if they moved when they were supposed to, if they knew they were supposed to move, if they've completed that on time. So when you've purchased that spectrum and you know somebody previously occupied it, spectrum clearing is an important time to make sure that all of that is clear in the different areas where you plan to use it. And then another example that we have going to spectrum monitoring. Recently, it's been announced that there have been auctions on the 24 gigahertz band for 5G. And a lot of my examples are 5G focused, and that really has a lot to do with the fact that a lot of the movement in spectrum over the last couple of years has been for changes in 5G and reallocation of spectrum. In this case, the need for this introduction of new 5G, the challenge that we have here is at 24 gigahertz, right below that in the 23 gigahertz band, you have weather satellite communications that are critically important for predicting weather patterns, or monitoring weather patterns and predicting weather for public safety and for national interest. And so what we see here is that as you have this new spectrum moving in next door, and you already own spectrum just below there, it's important or advisable for you to take some time and understand what the impacts of those might be and maybe do some spectrum monitoring to ensure that none of that signal is leaking into your bands. And then another example, also 5G related, but in a different band, in case you think that this may only affect the millimeter wave bands, we've seen in Asia where spectrum is allocated in the 3.7 to 4.0 gigahertz bands for 5G, but only given a 20 megahertz guard band next to critical satellite communications. So what you have here is you might have a satellite Earth station that's receiving signals from aircrafts from satellites, and now you have nearby a 5G tower that's transmitting signals at high power and coming across in that same airspace towards your antenna. And what they were finding in this specific example was that you have the cellular signal transmitting at 3.45 gigahertz, and then right next door in 3.9, where you have satellite communications, you have interference coming in and causing communication problems between the ground station and the satellites. So as spectrum shifts, as things change, as you get new neighbors, it's important to spend time doing spectrum clearing and spectrum monitoring. Okay, so talking a little bit then about what are the spectrum analysis tools that you would use for spectrum monitoring. On a high level, just thinking what is it that you want to look for in some of these tools. When it comes to hardware, weatherproof is something that can be important depending on how long or what your environment may be, something that can withstand the elements. And then also in general, when you're doing spectrum monitoring and spectrum clearing, ideally you're probably leaving an instrument in a remote location, allowing it to track data over time. So in some cases, in most cases, you're going to want something that can be controlled via a LAN or wireless LAN communication algorithm. So those are two things you want to see from your hardware. And on software side, things like trace and data recording so that you can see the changes in signals over time. Real-time spectrum analysis. The reason why this is important is that you can have intermittent signals that pop in and out of your bands, and a typical spectrum analyzer, no matter how fast it is, generally will sweep and then will pause sweep while it does processing of that sweep data, and then it will sweep again. And during that processing time, you may miss some of the signals and some important information about the interferer. With a real-time analyzer, they're specially designed to sweep continuously and process in the background, so you won't miss any signals, any interference that you have there. IQ capture and storage can be important here. This is for post-processing, which we'll talk about more later in this presentation, and channel scanning as well. If you are looking at multiple bands, you have multiple critical areas of communication, you may have tools that can help you do that rather than having to monitor one band for a period of time and then do it again and again and again. You may be able to, with a channel scanner, you can scan multiple channels as you go through your process of spectrum monitoring. Okay, so then that takes us to the next step after signal monitoring is signal identification. Now, identification is typically a step that is done on a higher level of interference hunting. Not everybody necessarily needs to do identification of the types of signal that's interfering. In some cases, it may be that all you care about is that there's an interferer and I want to stop it. And if that's good enough for your application, then typically signal identification is not something you need to worry about. But signal identification can be important for one, especially in nefarious cases when you're trying to identify what that interference is. It can also be a valuable tool in cluing you in how to find that signal or where it is. If you're doing analysis on a signal and you can look for things like patterns, is the signal repetitive? Are those repetitions long-term or short-term? Does it have common modulation scheme patterns when you look at things like the constellation? Is it random in amplitude and phase and frequency? So those are things that typically you're not going to learn just from looking at the spectrum sweeps, the traces from a spectrum analyzer. This is where you capture that IQ data and you go deeper, or you take that playback that you have of the signal and you slow it way down and see the nuances of the signal and what it might look like in a more granular resolution in time. So that's where signal identification can be extremely important. So this is typically done after the frequency and timing are known. So you've basically identified at such and such frequency, I've seen that I have this interferer, and now I need to go and capture it, and then I can go and do some post-processing. So typically done with signal playback, sample digitization, and vector signal analysis. So again, why is this important to do signal ID? In this example of you have a warfare or just a defense symphony shown here, what you might have, you have communications between hundreds or thousands of devices. Those communications are of extreme importance. If you start to see things like jammers that can come in and interrupt communication between aircraft, for example, going in deeper and understanding the behavior of a jammer can give you a solid leg up in mitigating the impacts of that jammer. So, for example, if it's some type of a smart jammer where as you're doing your communication, you see it with a spectrum analyzer, that jammer signal may be completely hidden inside the envelope of your radar pulses. But as you pull out the IQ and you slow down the playback and you look, you may see that jammer come in and start to track your radar. And as it tracks your radar, you're able to then zero in on what it's doing and then figure out its tracking algorithms and avoid them and continue to manage your communications in that way. So that's why signal identification can be extremely important. So what are some of the tools that you look for when you want to do signal identification? From a spectrum analysis side on hardware, typically you're going to need instruments that have higher performance hardware. So because of the sampling rates and the processing that's required to capture the amount of data to give you this granularity, you'll need faster sampling rates, which means you're going to need more processing capability. So typically these are going to be your higher cost, expensive, bulkier benchtop instruments, although handheld tools, which we'll discuss later on, are starting to catch up in some of those arenas and give you a chance to do some of that testing in the field. So software-wise, I've mentioned IQ capture, the ability to capture that or stream that data depending on how much. If you're doing tracking over a long period of time, capture is going to be limited to the amount of memory you have on that instrument. If you can stream that data out into external capture tools, then you have the ability to capture more data over longer periods of time and get more information about what you're looking for. Smart SIGINT tools, so with signal intelligence tools that can take that IQ data, some tools can actually use that data to give you clues about what type of modulation it is, and then it'll tell you what you can do. With that information, you now have a better idea of what the source might be. They can give you information about the patterns and repetition. You also have smart playback tools. So on the right-hand side of this slide, we're showing an example of SpectroX from XCOM. This SpectroX software allows you to take IQ data from a spectrum analyzer and replay it again at that granular level. It also has smart tools you can hunt through the data, tell it what type of signal you want to track. It will search through and help you identify those faster. It will help you trim the IQ data to get to just the portions that you want. So smart tools like that can give you a lot of insight on your interference. And then a last one I mentioned on here is audio demodulation. So a lot of spectrum analysis tools offer you an AM/FM tool that you can point to a specific frequency. When you get through to that frequency, you can then play back the audio in a demodulated as an FM, AM, USB, LSB type signal. And when you hear those noises coming through, now it may not be that you're hearing an actual audio signal that's transmitted, but you might hear some of the waves in the audio or clicks and pops. Things like that can tell you just what type of interference you're looking for, or random noise might let you know that it's something more random like an oscillator or alternator or something like that. So these tools are all very helpful in analyzing the signals. So I'm going to go through and talk about a hypothetical example just to show you the power of a tool that can capture IQ and do some playback. So this is a possible situation where you have charge over a specific set of spectrum and you are managing that spectrum with transmissions, but you started to get recent complaints about noise interference that's muddling up your communications or dropped communications. You may have done spectrum clearing early in the stages, but now you're going forward. You are you're looking to try to you're seeing things. You did spectrum clearing in early stages, and now you are seeing things later on that you didn't see when you did your spectrum clearing. So Just as the example, it may be, let's say that you are in charge, or your charge here is to be able to control this band in the shaded area, the shaded region. Now that band, in there you may have whatever type of communications it may be. When you go out to do some hunting, you find that using just a typical spectrum analyzer, you do see that just outside the bands that occasionally there is this sweeping signal that on a surface level wouldn't interfere with what you're doing. But as you go in and you capture that IQ data, or first let's say you look at it in an RTSA type of an environment, you start to see, wait, there's something else going on here. So you go and you capture that IQ data. And with the capturing of the IQ data, you now have the ability to take it and play it back in more granularity than you had before. So you see here, this is the same sweeping signal, but as you zoom in on the beginning of that tail, what you didn't see before was you have a sort of initial starting sweep within that radar that's coming in and now interfering in the band in which you're transmitting. Now, the manufacturer of that device may not know. In this case, this is actually just a little pocket radar device that anybody can buy off of Amazon. It can be used to test the speed of a golf swing or a baseball pitch, or oncoming vehicles. So it may be that in the vicinity of your transmissions, Saturday mornings, you've got baseball field, and you have coaches bringing out these devices and they're testing speeds and things. And during that time, you're starting to see drops in communications because maybe this device isn't transmitting exactly the way it should. So that's just a hypothetical example, but an example of what you might see in more detail as you get into signal identification. You capture that IQ and you go deeper into analysis on the interference that you're finding. The last step that we'll go through here is interference mitigation. So this is the last step in interference mitigation is location finding. So this is using those tools now to actually find the geographical location of that interferer, what's causing it, and then making a plan for shutting it down. So this is important because, of course, you can have all the information in the world you want about an interferer, but if you can't stop it, then it's really not all that much use to you. So you can this will help tell you whether the signal is hidden, or it may, in many cases, it's often unknown by the actual culprit of the interferers. One recent example that we read on the news was that you had somebody in a home in England, in rural England, who had a very old television, and every morning when they woke up and turned the TV on to listen to the news, these critical military communications were suddenly dropping left and right, and it took them months and months and months to finally locate and find that it was at this specific time in this specific house and this old television that was just transmitting signals out into the air and interfering with communications. So when is this done? This is typically done once you know you have an interferer, you have some idea of what type of interferer it might be, and you just do that through directional power finding. Examples we have here is on this instrument we have a directional antenna. That using a directional antenna, as you sweep through the air, you can track audio tones. Actually, skip over here to the next slide. You can have audio indicators. You can do drive tests as you do drives and start to triangulate the power levels of the signal interference. You can lay out on a map. If I go back to this previous slide, you see here an example where you start to lay out on a map and get an idea for, I'm seeing now the power levels are concentrated in a specific area. So typically what will happen is you'll do a drive test, you'll identify a hot zone, then you go park, pull out your instrument with a more directional antenna, and then search through that hot zone until you've tracked down the actual source of the interference. And that's exactly how, for example, the interference was found. That example that I gave you earlier of the store owner who had the LTE jammer in his shop. You might think that somebody could buy something like that and hide it behind, hide it in their back closet and nobody would ever know. But it was very obvious by the people searching for that interference, by triangulating the power. They had narrowed it down to it had to be in this shop, and they were able to get that owner to shut it down. So what are some of the spectrum analysis tools you look for? For one, you do typically want to have some type of a directional antenna, Yagi antennas or horn antennas. Some antennas also include compass integration. So as you point the antenna, what you can do is put these ley lines down on a map that tell you, okay, as I sweep through, I get the highest power when I'm pointing in this direction. You pull a trigger, it draws a line on a map, and then you go do it in multiple locations, and you start to triangulate now where that signal is, and then you can go in for further testing. Software type tools, real-time analysis can be extremely valuable in this case, especially when you have intermittent signals or TDD type signals that are bouncing up and down in time. With a real-time spectrum analyzer, you're going to get less variations in that amplitude and a better chance at hunting in power level changes. And then audio tones, as I mentioned, there are walk tests and drive tests available and mapping tools. So I'm going to tease one more time this example of a network operator who is seeing issues in their network. I'll come back to that in a second. I already mentioned again this nefarious source, the LTE jammer. So they used the directional antenna, they hunted down the interferer, the jammer, and were able to get it to stop. That's the overview of the general tools. I will take just a minute to introduce to you a product that Anritsu offers that does cover a wide range of these interference applications that we've discussed. This is our Fieldmaster Pro MS-2090A real-time spectrum analyzer. This is a handheld instrument that takes a lot of those benchtop functions that I talked about before and allows you now to take them into the field for spectrum monitoring and clearing, for signal analysis, and for power hunting. So what are some of the advantages here? The product does offer full coverage from 9 kilohertz to 54 gigahertz with different frequency models available. But that gives you, with no gaps, you now have the ability to look at spectrum in any position you want, to look for your interference in your bands, or even to check and ensure that you're not interfering in other bands. Fast sweep speed with a low noise floor, that's important because interference often resides at lower power levels. So with a lower noise floor and faster sweep speed, you're able to identify these intermittent interferers in a better way. It does offer the RTSA, the real-time spectrum analysis with a very low POI, which means the lowest signal that you're going to be able to get at full amplitude, and a 5 nanosecond minimum detectable signal. And then we've also integrated, or we have IQ capture and streaming, which I'd mentioned before has generally been a benchtop application, but the ability to take that in the field and use it while you're doing your spectrum monitoring. It's compatible with our remote spectrum monitor and our mobile interference hunter tools. And these tools, these are software tools that allow you to take that data, post-process it, and give you more information on your signals. And it's ruggedized for outdoor use. I mentioned spectrum clearing, so you can use your basic spectrum analysis tools. The real-time will help you see signals as they're moving, track signals over time, see anything that's sporadic. It does offer remote control for the spectrum monitoring application I talked about, and also a free PC software tool that basically gives you the user interface right there on your PC, so you can control that instrument from anywhere in the same network. And it's compatible with our tools that I mentioned before. IQ capture and streaming, so with a 32-bit resolution data and up to 110 megahertz of bandwidth, you can capture almost any signal. In general, most people are not looking to monitor more than 100 megahertz of bandwidth, so this gives you that full band. It gives you full information. Not only can you capture data up to 2 gigabytes of data on the instrument itself, but you can stream data out to USB drive. We've used 2 terabyte drives to capture data, or directly to the IQC5000B from XCOM, which allows you to capture up to 15 terabytes of data. For location finding, again, we can use the mobile interference hunter. Also, we have our interference finder, which is a directional antenna that you point and gives you an audio woo sound as you go through and look for the different signals. In our interference finder, you see here, this is an example where this is a signal on signal. With RTSA, with a regular spectrum analyzer, you're not going to be able to see that signal that's hidden inside that other signal. With RTSA, you can see signal on signal, and you can use the audio tones for greater power searching. Finally, just the solve on this interference that I've been teasing. So what it turned out to be was you had somebody in a rural area, again, who was not getting the LTE coverage that they wanted. So they purchased a repeater off of eBay, something that anybody can buy, but was not manufactured by a well-regulated or controlled manufacturer, which means that the signals weren't properly filtered. And so the uplink from one signal was interfering into the downlink of another and causing problems. And so using the RTSA, you see here that this was by hunting that down and looking at the power. With a regular spectrum analyzer, that wasn't possible because the signal was moving too much and the power levels weren't searchable. With an RTSA, they used a directional antenna, found the source, and were able to shut it down. The instrument also works with our PIM hunting tools. So I mentioned intermodulation issues. So if you have rooftops where you're doing transmitting and you're seeing issues, it could be because of things we mentioned, rusty bolts and cables, things that are left in the sheet metal that shouldn't be there. Those kinds of things can cause major problems with your signals. With the Fieldmaster Pro, you can also do hunting of those signals. Remote spectrum monitoring, we've talked a lot about. I also want to mention, you can check out our remote spectrum monitor, our MS2710XA. This product here is built with full weather protection, so you can leave that out. It's designed to be left out in the environment over long periods of time for doing monitoring. This is our mobile interference hunter, which I've mentioned a few times. This is a system where you have a PC with the software that controls all the data from the MS-2090A and an antenna on the roof. As you do your driving, you're able to map out the power of your data. You see here, this is a spectrum clearing where you basically draw a limit line and ensure that you do or don't cross certain limits, and then you can map out looking for interference. And that is basically all I have for you today in my presentation. So I think at this point we will go ahead and open it up for questions.
Great. Thank you, Russell. Let's see. Our first question is, what is POI in a real-time spectral analyzer, and why does it matter?
I guess I didn't go into a lot of detail there. POI stands for probability of intercept, and it's a general term to help define the performance of a real-time spectrum analyzer. And the reason why it's important is, if you think about, I mentioned before with an RTSA, you are always sampling and then processing in the background. But even when you're sampling, you do have some windowing effects, some filtering that's happening in the analyzer. And so we do overlapping of the signals to help diminish the effects of that windowing, but you'll always have a little bit of filtering effect that might take down some of the amplitude of your signal. So basically what the POI tells you is what is the minimum repetition of a signal where I will get full amplitude and no cutting off of that signal due to some of the windowing. And then the 5 nanosecond minimum detectable just tells you that because we have a 200 megasample per second sample rate, you get a 5 nanosecond minimum detectable signal.
Okay, let's see. What recourse does a system operator have when they discover an unauthorized user of its power and bandwidth, but the user is perhaps in another region or country where they refuse to stop transmission?
So recourse can vary, obviously, region by region. Typically what you have with neighboring countries is you generally have agreements between the government. So in the U.S., for example, the FCC has agreements with regulatory bodies with our neighboring countries in Mexico and Canada, and at some point it's in the interest of neighboring countries to behave well with each other. And so typically what happens is a carrier or a network operator, when they see interference, they use a spectrum analyzer or tool like that to gather data so that they can have the proof that they need to show that there are transmissions that are not allowed. They report that into the regulatory bodies of the country, and then from there it's generally handled at a higher level.
So in an interference caused by illegal terrestrial radio devices, is there a software application, a mechanism or system for detecting and identifying the number of handheld devices causing the interference?
Actually, counting the amount of them can be difficult from a spectrum analysis standpoint. Generally, what you will need is very smart software that can detect down to the level of actual identifications of the devices, and that depends on the type of transmitter, because not every transmitter has specific IDs. So if all you know is the spectrum, counting the number of transmitters will be difficult. You may have to do elimination one by one. If you can decode those signals to get actual IDs, you may be able to get more detail there, but you're getting into some pretty high-level signal identification in that one.
Okay. Our next question is, what would be common or probable external interference sources of 5G FR2 millimeter wave?
So common interference sources of the millimeter wave, so meaning that what would actually interfere with 5G. That one, I'll take this from both sides. What would interfere with 5G and what would 5G interfere with? The first one, certainly at this point, the millimeter wave spectrum feels much more like an open frontier. There hasn't been a lot of transmission or transmitting products in those frequencies, and the reason for that is that high-frequency transmissions or millimeter wave, for those who are not familiar, the millimeter wave is what we refer to as those higher frequency transmissions. Those transmissions, they have a much shorter propagation distance or a much higher propagation loss, and so they haven't been as popular in the past because it's much harder to get wide range communication. And so the generally what you might see with some of these are, I gave the example of that pocket radar, the consumer device, consumer communications, microphones, walkie-talkies, things like that. And now, though, as technology is becoming more available to process those millimeter wave signals, we think that there's going to be more and more people coming in and utilizing those bands. So not a high probability of interference today, but it will grow as you move along.
Okay, let's see. For spectrum monitoring, what is the equipment required, including antenna type?
It's going to depend a lot on your application in particular. In general, what we see with spectrum monitoring, you need some type of a scanning tool. I mentioned the spectrum analyzers that we offer, where you can place them out in an environment and leave them to gather the data. Then you're going to need some type of a network that allows you to pull that data in to be captured and processed. From an antenna perspective, that's harder to say. Generally, you're going to want something that is isotropic, so that in general, in that stage, you're not as much interested in direction finding as you are in just general interference in your band. So something that's looking omnidirectionally, and then depending on the power levels that you want to go down to, you may need some type of an amplifier included in your circuit. Typically with omnidirectional omnidirectional antennas, you're not getting a lot of gain in your signal. So if you're trying to pull things up out of the noise, you may want to have some amplification in there. And then as you're looking through that, you just make sure that you can account for that amplification then in your signal levels. And so those are the general tools that will help you get there.
Okay. What's the best antenna for power hunting and triangulating a signal? The person is using the MS2720T.
So I would say that for that particular application, you would use, we have an MA27000A. We call it our spot handle, and this is what I talked about before, where you have, it's essentially a handle in and of itself that contains a compass and then an RF port on either side. So you cable into the instrument, you run a USB to power the device, and then on the other side you can add filters and directional antennas. And then what happens is, as you search, the compass gives readings back into the instrument, in this case the 2720T Spectrum Master. The signal comes back in, you point it, and then when you see the power level rise to the highest peak, there's a trigger there on the handle. You pull that trigger and it will drop a line onto the map on your instrument, that's on your instrument. And then you do that from a couple of places, and then when you're done, you'll have, basically it will show, theoretically, if you have interference from one place, when you've laid your 3 lines, they should intersect at the point of your interferer.
And what is the sensitivity level of the Fieldmaster Pro MS2090A?
So we offer a down as low as minus 164 dBm. With RTSA, we do samples that are actually even lower than that. And then it depends a little bit on the frequency that you're trying to measure, and then trade-offs. When you're looking at sensitivity, the lower channel is always a trade-off in sweep speed. So or sweep speed or POI in the case of the RTSA. So as you're going down lower, you just want to make sure that you're not limiting your sweep speed to the point where you can't see your interferer anymore in case of intermittent interference.
Let's see, how many bit resolution is your AD circuitry?
I believe we use a 16-bit resolution.
Is the MS2090 good for locating wideband power line noise?
To be completely honest, I'm not super familiar with wideband power line noise in general. If I were to venture a guess based on experience, when we're talking about power line noise, generally you're going to look for I think that the RTSA is going to be a valuable tool in that case, because you're looking at something that's going to vary quite a bit in time and in power levels. So something like an RTSA tool could be extremely valuable in that case. The RTSA comes with a bit of a cost, so you may be able to get by with a more generic or lower level spectrum analyzer. It just depends on that type of interference.
Where is interference most commonly found?
Oh man, there's not. I'd have to say that there's not a very common. It's one of those. I don't know. It's one of those things where when you sit down and you talk to. If you have a chance to go out to dinner with somebody who does interference hunting for a network operator, a mobile network operator, or any type of network manager. And get them swapping stories. There's just a wide variety. That's why in that example slide earlier we had so many different pictures. It comes from a lot of different places. So, I would say that you're probably more often than not. I mentioned that you have random sources. It's either going to be intended signals that have somehow had wires corroded and are transmitting where they shouldn't, or it's going to be things like those low-quality electronics and or older, out-of-date products that have transmitted and it's never been a problem before, and suddenly it's causing issues.
Mm-hmm. Is there a standard rule about whose responsibility it is to protect against interference?
Well, as I mentioned before, it's a valuable and shared resource, a limited resource, and so everybody that has signals that are transmitting in the air has a responsibility not only to protect their own, but to make sure that they're not transmitting into somebody else's. The responsibility of fixing a problem will always lie on the person who is interfering outside of their own band. So, in the case of the jammer that we gave before, that store owner faced a hefty fine from the FCC if they didn't remove that, and now the incentive for that for that mobile operator to go and find that is that they want customer retention, and they want to be able to continue to provide good service for their users. So.
Okay, let's see. We have what is the best strategy? And I know you've gone over this previously, but what's the best strategy to find an interference source if you're in a congested downtown area where the source signal is pretty much bouncing all over the place and is hard to triangulate?
Yeah, this can be problematic in general, not only because signals can be bouncing around, but in urban environments, that your noise floor is going to be higher than when you go out into a much more rural, less populated area, right? You have a lot more thermal noise, you have a lot more component noise just from the general congestion of signals. This really comes down to expertise and experience. Not everything is going to be tracked down right away, but that's why the mapping, the initial step of mapping, can be really important, because while you may see some signal changes through things like multipath signals, things that are bouncing around the environment, with a map, you're still going to have hopefully some concentration of power near where that signal is transmitting. So even as it's bouncing around, if you've done a proper mapping of the area, you should be able to at least zero it down or narrow it down to an area where now you know that when I'm going out and doing my direction finding, I can ignore power from certain areas, because that's more than likely going to be some type of a multipath reflection.
You mentioned TDOA detection. Is the Enritsu equipment capable of making TDOA measurements?
Not every product, but some are. So, for example, I mentioned the spectrum monitor tool that we have, and that's typically done by tracking signals in time as you look at them synchronized to like a GPS clock. So as signals, you would place multiple monitors and you would monitor those signals over time, and you have all of the data from those multiple monitors coming back into a central hub, and you can then calculate the time and look at that type of thing. So not every product has that, but some do.
Okay. Looks like that's about all the time we have for questions today. I would like to thank Russell Lindsay for his presentation, and I would like to also thank our audience members for attending. Just a reminder that the webcast will be available on demand for 12 months at www.techbriefs.com. Thanks again, and have a great day.